Thanks for coming to the 8th PWLTO Toronto. Today we have Donny, who's going to talk with us about a consensus algorithm called Raft. Everybody give Donny a hand, please.
Thank you. I'm going to be talking about the Raft consensus algorithm, but before I get into that, I want to talk about why you would use a consensus algorithm and kind of what life looks like without using a consensus algorithm. So if you imagine having your application running on a single machine, a request comes in from a client, your application would handle it, and then you might look things up in a database and then respond to the client. And that works, and it's simple, but there are lots of things that can go wrong with that. So the machine that you're running on can lose power, or the hard drive can die, or the data center that you're in can be hit by a natural disaster. And all those things are at least going to cause your application to be unavailable and possibly going to cause it to lose data as well. So there are some things that you can do to try to work around that, like having multiple power supplies for your machine, or that there's actually a data center that is built in a repurposed nuclear bunker. So under 30 meters of granite, they have a data center. So you can do things like that, but they only take you so far. And even in the case of this data center, you have your machine protected, but the network that it's running on can still go down. So to really deal with these kinds of problems, you have to run your application on multiple machines in multiple data centers, ideally geographically separated, and you have to have multiple copies of your data. And you have to have your application work so that if any of the machines go down, your application as a whole is still up. To do that, you have to replicate your data and kind of reach agreement on how you're doing things, and the problem is that that's hard to do correctly. So one of the problems that comes up is when you have requests coming into different machines, you have to know which one happens first. If you had a request that was set the value to 4 and another one that said increment the value by 1, it matters which order you do those in. If you had machines do them in the wrong order, then they're going to end up in an inconsistent state. So you have to deal with ordering, and just in general, there are a lot of different corner cases that you have to kind of figure out how to deal with and make sure that you deal with properly, and it's really hard to do well. This is actually how systems were made before we had Patsos, which was the first proven consensus algorithm. What people had to do was they would come up with the happy path. It's easy. When everything goes well, their algorithms would usually work. But when things went wrong was where usually there would be some weird corner case that you wouldn't be able to handle. And there's actually a database in the 80s that made the claim that it could survive these kinds of failures, where you could have machines die, you could have network messages not be delivered, and as long as you had the majority of the machines up, then the database would still be up. And if you had more than that go down, then as long as you waited until they went up, everything would still be correct. So you might have unavailability, but you would never have things be done incorrectly. And Leslie Lamport, who's the creator of Patsos, heard about that and thought that was impossible. And he actually tried to prove that it was impossible, but instead he ended up creating Patsos and then proving that that was correct. So the problem that Patsos can help you solve, and in general that we're trying to solve now, is you want to have your single machine application and take that and run it on multiple machines so that they could fail, but your application is still working overall. One of the ways that you can do that is with a replicated log. So this is what Raft gives you, and this is what other consensus algorithms either give you directly or you can build it using them. A replicated log is just a log of operations where all of the machines get to see them in the exact same order. And it gives you a few other properties that I'll talk about a little bit later that make it easy to write an application on top of it. Normally, if you have your application, a client request comes in, it goes to your application, you might look things up, but then you would respond to the client right away. If you're using a replicated log, before you can do anything with it, you have to pass it off to the consensus algorithm first. The consensus algorithm is going to talk with the other instances of the consensus algorithm. It'll pass messages back and forth, and eventually they'll all agree on a value. And this is the part that I'll be teaching you about soon. once they agree on a value, then it will pass it back to your application, and then it's safe for you to act on that. So you can write it out to a database, or, by the way, for all these examples, when I say an application, this could be your actual application, although usually it would be a lower level thing, like it would be the database that you're using. They would do this stuff with the consensus algorithm, and you would just use them. So usually it's that kind of thing, but it is actually possible to do it for your entire application overall. It's just not very common. So once the consensus algorithm tells you that you can act on that operation, you do that, you write it out, and you respond back to the client. And if more operations come in, you can add them. And the guarantees that the replicated log gives you is that all of these operations are going to be in the same order on all the machines. So you never have one machine see x equals 4, followed by x plus plus, and a different machine see x plus plus, followed by x equals 4. The other thing it does is, once it tells you that it's safe to act on an operation, then you can go and reply to the client, and it will never tell you that you have to undo that operation. So that's being called committed. Once it's committed, it can never tell you to undo it, because you could have already responded to the client, so you can't undo that. The other thing that happens is that it guarantees all those properties while handling failures for you. So machines can go down, the network can have problems where messages are dropped, or delayed, or delivered out of order, or duplicated. All that kind of stuff the consensus algorithm handles for you, so that your application can remain mostly unmodified. Are there any questions about how you would use a replicated log to make an application, or to make it run on multiple machines? Cool. So, there are other consensus algorithms. The most popular one and the oldest one is Patsos, but Raft has some advantages. So one of them, that I think is probably the biggest one, is that with Raft, it gives you kind of the entire algorithm, including things like how you should detect failures, how you should deal with various other things that come up. Whereas with Patsos, with basic Patsos at least, it gives you only a small portion of that. And there are lots and lots of papers about how you can extend it to do these other things. But most often you have to kind of piece together the entire system from a bunch of different ways of doing things. Raft is used in a few newer distributed systems, like the ones I have up there, and they've tried to make it easier to understand than Patsos by especially making it intuitive why it's correct, and making sure that your intuitions about why it's correct are right, to the point where you should be able to take the algorithm and make modifications to it while you're implementing it, and be confident that they are correct. And they've actually verified this. One of the creators of Raft is a professor at a university who teaches a distributed systems course. And they ran a study where they created a Raft lecture and they created a Patsos lecture, and they gave them in different orders and quizzed them, and found that the students learned Raft more easily than they learned Patsos. One of the ways that they tried to make it easy to understand is by letting you break down the algorithm into a few different parts. So first I'm going to talk about leader election. In Raft, the way that they deal with the ordering problem is first you elect a leader, and then all messages have to go, all client requests have to go through the leader, so you can deal with ordering pretty easily. So first I'll talk about leader election, then the leader is responsible for replicating all of the data out to your followers. And then finally, I'll give a bunch of examples, walking you through the algorithm, and some failure cases, and we'll see how either it already works and handles that, or how I'll have to change my explanation to make it correct. So first, leader election. In general, with leader election, what you usually do is you do something where you request votes from all the machines, and once you get back a response from the majority of the machines, then you can be a leader. In Raft, they do something similar. But the way that you determine who should call the election, who should try to become a leader, is they use a randomized timeout. So they talk about the range 150 milliseconds to 300 milliseconds. So what you do is when you start up Raft, you pick a number in that range, and if you go for that long without hearing from a leader, then you try to become a leader. There's also this term up here, which I won't explain right now, but it should make a little bit more sense why we need it later on. But in Raft, you don't just become leader forever, you become leader for a specific term. And the invariant that we want to guarantee is that you never have two leaders for the same term. So let's say server 2 times out first. What you do when you want to start, when you want to become a leader is you increment your term and you persist it. Then you send a message. Then you send a message requesting votes, and you can send it to yourself and the other machines. And it may seem a little bit weird to send a message to yourself, but the implementation actually can be easier if you do it like that. It's a bit more elegant if you deal with everything like that. Just send a message to yourself, and you deal with it like any other message that you would get. So you send a message to yourself, requesting your vote for term 1. And right now, the rule that I'll give you is if somebody requests your vote and you haven't voted for anybody yet, then you grant them your vote. I'm going to have to extend that later on, but for now, we'll use that rule. So you've requested your own vote, you respond to yourself, and when you get that response, you record who has voted for you so far for the term. You've also sent out messages to the other nodes. And one thing is that in Raft, every message includes this term number. You just include the current term that you know about. And when you get a message, if it has a higher term than yours, then you kind of reset your state. You update the term and you persist that. You forget about whoever it was that you had voted for before, and then you respond to the message as normal. And also you ignore any messages that come with a old term, so anything less than your current term. So we've requested the votes, we've updated our term, we record who we're going to vote for, and then we send a reply back saying that we've granted the vote. And in this case, imagine that there's a network partition between server 1 and 2, so the message from server 1 can't get through to server 2. But the message from server 3 gets through, so we record that we have voted, or we record who has voted for us. And now at this point we have 2 out of the 3 nodes in the cluster who have voted for us. So at this point, we are the leader. So I'll explain a bit about the term, which is that it is possible to have multiple nodes who think they're the leader at the same time, but it won't be for the same term. So for example, server 2 could be off on its own, it thinks it's the leader, but maybe it's running really, really slowly. The other 2 machines could hold a leader election. One of them would increment its term to term 2, hold the leader election, and get elected leader. And you would have multiple machines who thought they were the leader, but one of them has a higher term. And the point is that you would never have multiple for the exact same term. Any questions about leader election? No? Cool. Once you have a leader, so first of all, as I mentioned before, all client requests go through the leader. So if a client can contact any Raft node at all, and what they're supposed to do is, if they're not the leader, then they tell the client who they think the leader is, and then they have to go and connect to the actual leader. So requests come into the leader, and it's up to the leader to replicate the data out to its followers. So the way you do that is once you receive a request, first you write it out to a log. This is just a file. You persist it to a file, and you send out messages to all of your followers. And what you send them is the piece of data that you want to replicate, the current term, just like in all messages, and you also tell them about the entry in the log just before the one that you're sending them. So you tell them what the index is of the log just before the one you're sending, as well as the term of that log. And what the followers have to do is they have to compare that information to their own log. And if it matches, then they put it in. And if it doesn't match, we'll cover that in a failure case after. So once the followers have put that into their own log, they can reply to the leader. And once the leader has received your replies from the majority of nodes for an entry in its own term, then it can consider it committed. And that restriction about it has to be for an entry from its own term, we're going to go through a failure case later on to show why that needs to be true. For now, just trust me. So once you have committed the client request, you need to, then you're allowed to apply it. So this would be, if you're a database, you would go and write it out to a file, and you can also reply to a client that it's done. I also want to clarify a few terms first. So one of them is once you've added something to your log, even though it's persisted to disk, that doesn't mean anything on its own. What I mean by that is you can have log entries that you put in your log, you persist them, and they get overwritten later on. So adding it to the log doesn't mean anything on its own. It's only once it's been committed that you can consider it final. Once it's committed, then you know that no other entry will ever be put in the same place in the log, and that as long as the machines stay up for long enough, that entry that was committed will eventually be propagated to all the other nodes. Once you have something that's committed, you're allowed to apply it, and that just means acting on it, replying to to the client. I also want to make a distinction between when something is actually committed and when machines find out that it's committed. I think that a useful way of thinking about when something is committed is something is committed when you could look at the state of all the machines, of all the messages that are in transit, and knowing the rules of the Raft algorithm, you would be able to conclude that that entry will eventually be propagated to the other machines as long as they're up for long enough, and that entry will never go away. And that's different from when machines find out that something is committed. That happens later on. So something can first be actually committed, and then machines find out about it. So I'll walk through an example and point out when those things happen. So we have server 1 is the leader. On the right-hand side is the log entries for all the different servers. And let's say a client request comes in. First, we append it to our log, and I'm going to use gray for things that are appended to the log but not yet committed, and green will be committed. And A is just an arbitrary piece of data that the client is writing, for example. So we add it to our log. We send out messages to all of our followers with this append entries call. So it was what I described earlier. You have the data, the current term, a bit of information about the log entry before the one there, and you also have another piece which is the leader commit index. So this is just telling followers how many things are committed so far. One thing you might notice is that the indexes and the term are one-based, and this is from the paper. So the first term is term number 1. The first index is index number 1. So telling somebody that the previous log index was 0 means that there was nothing there before. So we've sent out messages to all of our followers. Let's say it gets through to server 1. Sorry, to server 2. We append it to our log, and then we reply to the leader, or we begin to reply to the leader that it was successful. Let's say the next message goes through, and it gets to server 3. Now, at this point, server 3 has added it to its log, and at this point, I can tell you that this entry is committed, because I know that if you follow the rules of Raft, and given the state here, that A is eventually going to be propagated out, and that it is impossible for anything other than A to be put there. It's only going to be A, guaranteed. But none of the machines here know that yet. The leader only knows that it has sent out messages to its followers. It doesn't know how many of them have got them. And all the followers, they've either gotten one message or none. They don't know about any of the other followers either. So right now it's committed, but nobody knows it's committed yet. Server 3 would reply to the leader. Let's say the message goes to server 4, we add it to our log, it starts to reply to. And now let's say that the first message from server 2 gets to server 1. Right now the leader knows about 2 nodes that have the entry itself and server 2. That's not the majority yet. You need 3 out of 5 for an entry from your own term, so it's not committed yet. Once the entry, or once the reply from server 3 comes through, at this point, server 1 can mark that that entry is committed. So I'm marking that with green, and then because it's committed, it's safe to actually apply it, and you can reply to your client. Let's follow through. The message gets to server 5, they put it to its log, and servers 4 and 5 reply. And this message, it's not exactly discarded, but it doesn't really change anything. The leader will update to keep track of how many things its followers have, but in this case, we already knew that it's committed, so it doesn't really change anything. Are there any questions about this example? And by the way, I'm going to have a bunch of different failure cases coming up, So feel free to ask, but I may tell you that it's covered later. I think Glauber, I saw your hand first.
So you said that the state is committed when S3 gets the message, but it doesn't have to reply to server 1 for that to be committed?
Yep, so it's committed when server 3 gets it. By the definition of something is committed, if you can look at that and know that eventually this is going to happen. So I consider, like me, Donny.
No reply there yet, right?
Yeah, I consider it to be committed, but none of the machines know that it's committed until they get the replies. That's when they find out that it's committed. But something being committed is kind of a property of the entry itself, or a property of all the logs and messages together. Another question?
Why keep track if, once you reach quorum, why keep track that S4 and S5 got it?
You keep track of it. So the question is, why keep track of the fact that server 4 and 5 got it? What you keep track of is the index that your followers have matched you up to, because next time you go to send a message, if server, actually I don't have a good example in my head, but it can be helpful to know that they have it.
So you can replay old ones.
Replaying is done a little bit differently, but in my implementation at least, I used the information of what entries nodes had to determine what things were committed. To find out what things were committed, all you have to do is just sort the entries by index and take the middle one, and that's the index of things that have been committed. More questions? All right, let's go into some failure. Oh, sorry, a little bit more here. Right. So at this point, the leader knows that it's committed, but none of the followers know that it's committed. There are 3 different ways that they would be able to find out that it's committed. One of them is if the leader fails, then one of the followers will try to take over and become leader, and it would find out what index things were committed up to. I'll show that example later on. The 2 normal case examples are, the first way is a new client request could come in, and when you're sending out that new client request, you're also telling your followers what index things are committed up to. And so they would simultaneously get that new entry and find out that the previous one was committed. I'm going to show that in the next example. The one that I'll show now is that server 1, the leader, has to regularly send out heartbeats to its followers. It has to do this to prevent them from timing out and starting an election. So in Raft, what they do is they reuse this append entries command as a heartbeat command. Because in the append entries command, you can actually pass an array of entries to append to the log. You can pass multiple at once if you want. Or for the heartbeat message, you pass no entries. So in this case, you do an append entries call, you pass in an empty array of things to append, and you also give them the leader commit index. So once they receive it, then they know that server 2 knows that the entry was committed. Same with all the followers. More questions before I go into failure cases? All right. First failure case. Server 1 is the leader again. Client request comes in, and we go to send our append entries command to the other nodes. First we append it to our log, then we send it out. But there's a network partition between servers 4 and 5. So if server 1 tried to talk to them, it can't, so I'm not even going to bother showing the arrows. Just assume there's a line there, they can't talk to it. So it sends out this append entries command. Its followers, servers 2 and 3, add it, and then they reply. You mark it committed, and a new request comes in. And let's say that the network error or whatever happened goes away. Server 1, the leader, will append it to its log, and it will send out a message to all of its followers, and I'll show these ones first. The problem here is that they're getting an append entries request for an entry where they don't have the previous one. So this is the part that I talked about before, if you have to match your log against what the leader is telling you. So in this case, the leader is telling you that the previous log index was 1, and that the term of the entry there should be 1 as well. Because you don't have an entry there, what you have to do is you have to reply false to the leader, that you didn't append the entry. In response to that, the leader will then send you the previous entry in the log. And in this case, they also simultaneously get that entry and already know it's committed. Another thing is that in the basic Raft algorithm, at least, they don't have any kind of optimization around this. So if you had multiple entries that you were missing, let's say it was entry D, and your follower says, I didn't get it, you go back and you send entry C, and it says, no, I didn't get it, entry B, no, I didn't get it, finally A. So it just goes linearly back there. And there are pretty simple ways that you can optimize this, but in the basic explanation of the algorithm, they don't do that. So now it would add the entry, more, yep. And this is a continuation of kind of where the last example was, where we have servers 2 and 3, they have an entry that they don't know is committed, a new client request comes in, and they simultaneously find out that it's committed and get a new entry. Yeah, they reply and mark it true. Any questions about this example? No. Cool. Another example, server 1, and we have a network partition from server 5. Client request comes in, we add it to our log, send it out to all of our followers, they reply back, we mark it committed, and we reply to our client. Now at this point, imagine that server 1 dies, and that server 5 times out and tries to start an election. So it would send out request vote messages with term 2, it would increment the term. And with the rule that I gave before, if you haven't voted for anybody yet, then you vote for them. Under that rule, they would reply yes, and server 5 would be the leader. And the problem with this is that a client request could come in after, and maybe this was asking for the data in A, or was an operation like increment the value in A by 1, and it wouldn't be able to reply to these properly. So some consensus algorithms deal with this differently. Some of them do it where when you become a leader, you also have to find out all of these old entries and have them be replayed from your followers, different things like that. In Raft, what they do is they add a restriction on the leader election protocol. So what should happen is you add in some information about the last log entry that you have, so the index and the term of it. And what you do is you only grant your vote to someone requesting it who, first of all, you can't have voted for anybody yet, but also you only grant it if their log is at least as up to date as yours. And the way that you determine that is by first comparing the term of the entry, and if they have a higher term, then they're more up to date, or if the terms are equal, then whoever has the longer log is more up to date. So in this case, what should happen is server 5 would send a request. It would say that it doesn't have any entries, and servers 2, 3, and 4 wouldn't grant their vote. And so eventually, one of those ones would become leader instead of server 5. Any questions about this? Oh, sorry, question.
In the last case, won't server 2, 3, and 4 vote for themselves first before voting for anyone else? Won't that be?
Won't they vote for themselves first? Yes, but it depends on when they time out. This is part of why you have a randomized timeout of when you haven't heard from the leader in a while, because one of them should time out first.
Okay.
Even if multiple time out at the same time and vote for themselves, then that election, if in term 3 everybody votes for themselves, nobody can become a leader for term 3. But eventually, one of them is going to time out first, and it's going to be able to get most of the votes. More questions? So another example, server 1 is the leader, all the nodes have an entry and they all already know that it's committed. Client request comes in, we add it to our log, and we send it out to only one of our followers, and then server 1 dies. Let's say that server 3 tries to become a leader, and it can because servers 3, 4, and 5 would vote for it. They all have the same log in this case, and the rule is that you vote for somebody who has a log that is at least as up to date as yours. It doesn't have to be more up to date. So server 3 can be the leader, client request comes in, and we send it out to all of our followers. In this case, servers 4 and 5, they had nothing there, they add it to their log. But when we send it to server 2 has a log entry in the way. It already has log B. And the question is, what should server 2 do in this case? And the answer is that in Raft, if the leader tells you to append an entry, then you do it. So if you have something in the way, you delete that entry, and anything that was following it, if it was following it, and you add the other entry instead. It's always safe to do this, because entry B wasn't committed. If entry B was committed, then it would have had to be on the majority of nodes, and if it was on the majority of nodes, then the new leader would have got it. So the leader can always tell you to delete entries, and it's never going to tell you to delete a committed entry, at least if you've implemented Raft bug-free. Any questions about this? Yep.
What is it that makes it so that the leader must have gotten it if it was on the majority of nodes? Just because everything had to have gone through the leader, and
why does the leader have to have it? Yes, because if something was committed, it has to be on the majority of nodes. That's not sure what exactly that proof is, but yeah, a necessary but not sufficient condition. So if it's committed, it must be on the majority of nodes. If it's on the majority of nodes, in order to become leader, you have to talk to a majority of nodes. So if it's on the majority and you don't have it, none of the majority will vote for you. You won't be able to become leader. Only one that has that entry will be able to become leader. Any more questions? Yeah.
If the leader dies, and then some other machine which got the message dies, then it becomes the minority have received the message. But then the new leader can elect, but it was already committed. What happens?
So if you have a leader that gets the message, it only sends it to one other node. Both of them die.
No, leader gets the message and it sends it to majority, gets a reply, commits it, and then dies.
Okay.
Okay, and then the next message comes in. Before a leader is elected, but some other machine also dies, which originally had the message. So now the minority have a message, and they get voted out.
Okay, so if you had a leader gets a message, or it gets a request, sends it out to, let's say, only the majority, so we only have 3 out of 5 that have it, they reply, it's committed, we send it out, leader dies, and one of those other nodes dies.
Right.
What we have left is 2 nodes that don't have the message, and that have the latest entry, and one that does have the latest entry.
Yeah.
When you do a leader election there, you still have to get 3 out of 5 votes. You're not looking for the majority of votes from live servers, you're always looking for 3 out of 5.
Oh, I
So if
see.
you have that situation, any of the ones that don't have it, they still have to talk to everybody there so they can become leader. More questions? Alright. Last example. We have, and for this one I'm going to have to introduce terms as well. I'm just going to write down the current term next to the leader. So a client request comes in, we append it to our log. And in this case I'm going to extend our notation to be the term and then a pipe and then the command. So one pipe A is the command A, which was from the leader of term 1. So request comes in, we add it to our log, we send it out to one other node, and then we die. Server 5 becomes leader, and it can because servers 3, 4, and 5 all have an empty log, so they would all vote for it. Client request comes in, 2B, and we send it out. Oh, we don't send it out, we die. Server 2 becomes leader for term 3, and it can because it has an entry in its log. Servers 3 and 4 don't, so server 2 has a more up-to-date log. So servers 2, 3, and 4 would all vote for it, so it can become the leader. It gets doesn't get a client request. It continues replicating the entry here. So I won't go into detail about how this can happen, but one example is with the heartbeats before that you're sending out. If it was missing, if it did a heartbeat here and the machine was missing an entry, then it would send it the previous entry. So you can have this situation where you're kind of replicating entries from a previous term. So it sends out the message to append the entry to servers 3 and 4. They get it, add it to their log, and they reply that they have it. Now at this point, server 2 has the entry. It knows that servers 3 and 4 also have the entry, so it knows that the majority of nodes have it. Now the question is this entry committed now? And the answer is that it is not, because it's not from the current term. The reason why you can't consider this entry committed is because you can imagine server 2 could die, and maybe some of the other ones come back online, and server 5 could try to become a leader. And if it did, any of the other machines would vote for it, because when you compare to see whose log is more up to date, first you compare the term of the last log entry, followed by the index. So because server 5 has a higher term for its last log entry, any of the other nodes could vote for it, it could become the leader, and it could tell the other nodes to overwrite the entry that it has there. So because it could be overwritten, you can't consider it committed. There isn't really a change in the Raft algorithm to deal with this. This is just kind of an explanation of a complicated case that can happen. One of the ways that you often deal with it, though, is, I don't think they talk about this in the paper, but maybe in the thesis they talk about it, is a common thing is once you become leader, you append a no-op operation to your log, and you try to replicate that out. Or you could just wait for a client request to come in, but it's easier just to always append a no-op right when you become leader. If server 2 had done that and gotten the majority of nodes to have that entry, then the last log entry would be an entry from term 3, which means that you would block server 5 from being leader. And by replicating an entry from your current term, you can then mark it committed, and everything before it is also committed as well. So that's the way that a new leader finds out that things are committed. It just commits one more thing, and then knows that that and everything before it was committed as well. The reason why, by the way, why you can consider something committed from your own term, but not in this, is because when you have an entry from your own term, and you hear back from the majority of nodes, you get a bit of extra information that you can infer about the state of other nodes. So not only do you know that the majority of nodes have it, but they're also telling you that they didn't vote for a leader in between, so a leader couldn't have stuck another entry before yours or have another node that has it there. So because you know that that hasn't happened, it's safe to commit it when it's from your own term. This is the end of the examples that I have. So are there any questions about failure cases before I move on?
So just so I'm clear, so S1 and S5 are dead.
Yep.
S2 has been sending out heartbeats to all the nodes it knows about. It
Yep.
found out that S3 and S4 were behind it, and so it replicated what it did know out to S3 and S4, but that wasn't committed because it's not the current term.
Yes, that's right.
Okay.
You've got it. More questions?
When leader election happens, does it look at the committed logs or just before it's committed?
It doesn't look at, so when you have a leader election, you send out the entry of the last log entry that you have, or the information about that entry. It doesn't have to be committed. What you're doing is you're sending out information about the last log entry, which is things that are committed and things that might be committed. And you guarantee that a new leader has anything that is committed and even anything that might be committed.
So when leader election happened over here, S3 and S4 had no chance of becoming leader because S2 had more.
Back here, that's right, S3 and S4 could not have become the leader because they would vote for each other, but you need the majority, and none of the other nodes would vote for it because it doesn't have more up to date, or it doesn't have a log that is at least as up to date as theirs.
Unless all the other ones died. Before they're
Even if all the other nodes died and the only remaining ones are S3 and S4, they can't form a majority. One of them could do a leader election, it votes for itself, the other one votes for 2. You only have 2 out of 5 nodes.
Right.
You're always comparing to how many nodes are in the cluster, not how many live nodes there are.
right.
And this is another thing that in Raft you can have unavailability like that if you have the majority of nodes go down, but they favor consistency over availability. So if you have that situation, sure, your Raft cluster might be unavailable, but it's never going to do the wrong thing. It's never going to tell you things were committed when they shouldn't have been. It's never going to let you think things are committed when other nodes could come back on, or those ones could die and other ones could replace them and it's gone. Yeah, it's always consistent, but maybe not available. All right, there's more pictures. One thing that I've been doing so far is just using kind of the very vague term, a client request comes in. In reality, a client request is either a read or a write. With a write, it's fairly obvious that you have to push this through the consensus algorithm because that's how all of your machines find out about the data. But with a read, what some people think is that you can just check to see if you're the leader, then you must have the most up-to-date state, so you can just reply to a read directly. But you can't. That's incorrect to do. The reason why you can't do that is because you could have a node that's the leader, and then let's say the rest of the cluster is separated from that. They start operating really, really quickly, or maybe the leader starts operating really, really slowly. The rest of the cluster could elect a new leader, have new client requests come in, write them, handle them, even respond to the client. All the while, you have two nodes that think they're the leader, this old one and the new one. A client could go and ask to do reads from the new leader and get responses back. And if it asked the old leader for reads, then the old leader would respond too, but now you get new information followed by old information. And you should never have that. One of the properties that Raft gives you is linearizability. I won't go into detail, but that would violate that property, so you can't do it. This is actually a mistake that the etcd project made. They didn't have reads go through consensus, and as a result, you could have stale reads where you read some new information followed later by reading old information. The way that you have to deal with reads is one easy way would be just pushing them through the consensus algorithm as well. Send the read operation through, it'll get written out to the log, but that's a little bit wasteful because right when you, after you've written it and you respond to your client, you don't need that anymore, so you're kind of wasting space. A correct but more efficient way of doing it is instead what you want to do is when you get a read, you hold on to it, and then you send out a message to your followers with just a heartbeat message. And what you want to find out is, was I still the leader at the time I got this client request? And so if the majority of the nodes reply back to your heartbeat that you're still the leader, then you can respond to that client. And you can also make this a bit more efficient where you can batch up reads. You can get 100 reads at once and send out a single heartbeat message to your followers. Once you get it back, then you can respond to all 100 clients just from a single Raft message. The cost of this is that you have to wait for one round trip time to your followers. Any questions about this?
You can surely respond to a read that you were sure to be committed, right, from an older time.
Can you respond to a read that you know has been committed from a little older time?
And
No,
not that it's committed by
because
the protocol, but you as the node know it is committed.
yeah, so the leader knows that a bunch of things are committed. If you get a read for one of those things, you still can't reply if you think you're the leader because the rest of the cluster might have moved on and committed new things that change those. If you were to allow this old leader to reply to requests, you could get old information. So if you imagine you have a node where it only gets a single committed entry and then it's off on its own and paused kind of, and then years go by and the rest of the cluster goes further and further ahead. If you were to ask that old entry for things that happened in the new cluster, it wouldn't know about them. It would tell you it didn't exist. So you can't do that. You have to push reads through the consensus algorithm in some way, either directly in the log or by asking followers. Yep.
While you're asking followers, since you need to wait for, I guess, a majority of followers to tell you that you were the leader when you thought you were,
Yep.
Because that takes time for all of them to respond, could there not be a race condition where, someone else is doing the same thing and you end up with an old following a new,
So you can kind of get that situation. All that it tells you, you get a request, you ask your followers, am I the leader? By the time they reply, another leader might have been elected in the meantime. The only thing that you know from that is that you were the leader at the time you got those requests. You could have network latency have kind of weird effects like you said, but one property that doing it this way and pushing reads through the algorithm would give you that reading directly wouldn't is if you had a client that issued operations purely in serial. So they sent an operation to the cluster, to the Raft cluster, and waited for a reply before they sent a new one. Using this, pushing out reads through the algorithm, you would never be able to have old information like that. if you have clients that are issuing requests in parallel, then you might have stale reads even with pushing things through the algorithm. But if they're doing it in serial, you're guaranteed that you won't. But you don't have that guarantee if you don't push them through the consensus algorithm in some way. More questions? Yeah.
Can information in an index change? Is that what you're saying?
Can information in the index change?
Yeah.
I'm not sure what you mean by that.
Why can't no leader reply to something that's committed? Again, the same question.
Sorry, I'm not sure whether I understand the question. Can we talk after maybe?
Okay.
Okay. Another question? Oh, okay. I'll address more after. Another thing that I want to talk about is right now we've been talking about a cluster with kind of a fixed membership. We have 5 nodes. All the members know about these nodes and they never change. But in reality, you might have some nodes fail and you have to replace them by removing the old node and adding a new node. Or maybe you have a cluster that has 3 nodes and you want to change it to 5. In the paper, they talk about this approach that they have called joint consensus, where what they do is when you want to make a change, you have to remember both the old and the new configuration, and you have to kind of act on both of them and make sure that they're in sync. And that works, but it's a little bit complicated. The reason why they thought they had to do that, at least, was because if you allow nodes to directly go from the old to the new configuration, then one of the failure cases you could have, for example, is if you have a cluster with 3 nodes and you want to change it to 5, you could have 2 of the nodes off on their own. One of them is the leader, the other one is the follower, and then you have this other follower on the side. If you say that there are now 5 members, that follower off on the side now has 2 new followers. It can ask for votes. So you have the leader over there with 1 follower, and the other original member could ask for votes from these 2 new ones, and you could end up with multiple leaders for the same term, which we want to ban. Now, in the paper, they made the claim that you can't directly switch from the old configuration to the new configuration, and that it's inherently unsafe. And when I read that, I kind of put a mark next to it and wrote, "Oh, really? Challenge accepted." So I thought about it for a while and came up with the idea that if you did membership changes one at a time, or if you wanted to do a larger membership change, you would do it as a series of single node additions or removals, then I thought that would work. And I thought about it more and kind of convinced myself that it was right. And I was getting ready. Yeah, sorry, question.
Go ahead.
Yes, I'm about to talk about that. Don't worry. So I came up with this brand new idea that nobody had thought of, and I was preparing to email the authors with a more formal description of it. But then I did a quick search and found that a few months before, one of their colleagues had already came up with this idea, told them about it, and convinced them that it was a better way of doing it because it's simpler. So if you read the paper, you can read about joint consensus if you want, but there is a simpler membership change algorithm, which is just single membership changes, so you can read about that instead. Some of the, was that what you were going to comment about?
Well,
Or do you have another comment?
is that considered a direct change from the old to the new configuration? Because they say direct.
You do a direct change, yes. So,
But
right when you get the message, you act on it and you act as if you're using the new configuration. But the only change you're allowed to do is a single node addition or removal at a time. But you do directly go from the old to the new, whereas in joint consensus, you have to remember the old configuration and the new configuration. And when you're determining quorum, for example, whether something is committed, you have to check, is this committed with the old configuration and committed with the new configuration? Okay, then it's committed.
But the difference is that when you limit the allowed configuration changes, it puts like single changes, so that you can get around this.
Right, it is limiting, but you can do any arbitrary change as a series of one node changes, so it doesn't have a real limit, although a mild performance one. Yep.
So when you're doing single node changes, you have to wait for the whole cluster to recognize the change? Does that what it means to do it in series? Or?
I don't want to go into the full algorithm, but you don't have to wait for the entire cluster to do it, just the majority of the cluster, similar to commitment. So some of the limitations of Raft that I want to talk about. One of them, a failure case that we haven't really touched on right now, is you have this cluster that is supposed to be highly available. supposed to be able to have machine failures or network failures, and it's still up as long as the majority of machines are up. But there's actually a case where you can have a single node that's misbehaving or a flaky network, and it can cause your entire cluster to be unavailable. So if you have, let's say, a really bad network connection just to one of the nodes, what's going to happen is it's going to frequently time out, try to start an election, increment the term, send it off to the other people, and they're going to stop following the leader because there's a new term. They're going to forget who they voted for, and when the leader gets that message, it's going to forget it was the leader because it's a brand new term. In an extreme example of this, if you were using UDP to implement your messaging, for example, and you had misconfigured your firewall so that you allowed outgoing messages but no incoming messages, then you could have a node that is sitting there constantly incrementing the term, or whenever it times out, and sending out messages to all of the followers, disrupting the cluster basically permanently. In the paper, they don't talk about a way of dealing with this, but in the thesis, they mention that there's no real perfect way of dealing with this, but one way that they came up with, which I think solves basically all practical considerations, is you can introduce a phase before leader election. So what you can do is, before you're allowed to increment your term and send a message out to all of your followers, you have to send out a message to all the other nodes saying, if I were to increment my term and ask you for my vote, would you vote for me? And then once you get replies from the majority of those, then you can actually increment your term and start a real leader election. So in most cases of network instability, you wouldn't be able to get through that pre-election phase. Another problem that Raft has is you can have a slow leader. So if you have a node that is so bad that it can't send heartbeats, then one of the followers is going to time out and start an election. But if you have a node where maybe performance degrades and the leader is only handling 20 requests a second, but if a different node was leader, then it could handle 1,000 requests a second. First of all, you wouldn't even know that that was the case necessarily. It's not straightforward how you would do that, especially if the commands that you're running can run in various with various resources. You know, maybe you're just getting really intensive commands, so you can't easily tell like that. There is a different consensus algorithm called egalitarian Patsos that doesn't have a leader, and that can deal with this pretty easily because you can ask any node to perform operations. And so you can just, if you detect one of them as being slow, you ask a different one. In Raft, the only way that I could think of was to deal with this was either doing a lot of work to monitor performance and kind of detect this, and then ask another node to be the leader, or maybe rotate leadership around every once in a while just to try out different nodes to see how they would do, but there isn't a really good way of doing it. Another thing that they don't talk about in the paper, but they do, actually I don't know if they talk about it in the thesis either, pipelining of operations, where you can extend Rafts that you can have multiple messages in transit to a node at the same time, and it can be kind of efficient. I did that with my own implementation, and it was fairly straightforward to do, but they didn't really talk about it, how to do it very much. One that they do talk about is log compaction. So right now we have this log of operations that grows without bound. Even though the application state might be pretty small, we have this log that keeps on growing. And I won't go into detail, but it's fairly straightforward to deal with. You just have to, every once in a while, snapshot your application state, and then you can discard most of the log. Any questions about these? Cool. Quick comparison with Patsos. One of the criticisms of Patsos is that there are a lot of different variations of it, and there are a lot of different options where you have to kind of piece together what the whole version of multi-Patsos is from different little bits and pieces. One thing that I think that Raft does get right pretty well is that it doesn't have a lot of subtlety in the algorithm. It's fairly straightforward, and I implemented some modifications in my algorithm, of the Raft algorithm, and I at least think that they're correct. So that they might not be, but it is at least easier to believe that you're right about modifications, or possibly even easier to make correct modifications to it. I think it is actually easier to make correct modifications, but who knows. Some other things are egalitarian Patsos I mentioned earlier. It's a pretty cool algorithm. One thing that I'm not going to talk about much is Byzantine fault tolerance, which is right now we've been assuming that network messages can be dropped or delayed or delivered out of order and machines can crash and things like that, but the messages aren't allowed to be corrupted or changed. And on top of that, nodes aren't allowed to lie to each other or do the wrong thing. Whereas in Byzantine fault tolerance, you don't assume any of that. Nodes are allowed to lie to each other, to give each other inconsistent information, and there are Patsos variants that solve this problem, even with these nodes that lie to each other. But there isn't yet a Raft implementation for it, although I think that there's one kind of in progress. A few tips if you do want to implement Raft. One of them is that you're probably not going to get it done in a few hours in an evening. It takes more like a weekend or maybe more, depending on how in-depth you want to go. So expect it to take a while. One thing I did that I think was really helpful was adding a fake networking layer. So in my implementation, I used message passing rather than synchronous RPCs. And I just made a list I made a method where you could call it and pass in what your ID was, what the ID of the node you wanted to send it to was, and just the instance of the message that you wanted to pass. And I added that to a list, and I had methods where I could print out what was there, drop them, you have access to the list so you can reorder them. It made it really easy to test out different various scenarios, and if you added a lot of logging, then it's pretty easy to follow along what's happening. I mentioned before that it's one-based indexing. If you want to make it zero-based indexing, which I did because zero-based indexing is nice, you can do it, but you have to initialize any index or term variable to -1. Otherwise, your implementation will be wrong. Message passing. If you want to do message passing instead of remote procedure calls, you can. You just might have to add a bit of information. For example, the append entries reply. You have to send back a bit of the information that you were given. Another really kind of specific one is that in my implementation initially, nodes knew about their ID, and I just called that variable ID. But then in a lot of different places in the code, you have other IDs there, and sometimes they were called ID as well. And I spent a lot of effort kind of trying to make sure I wasn't shadowing the variable and using the wrong one. And I had a close call where I almost introduced a bug because of this problem. And I thought, why am I doing this to myself? Just rename it. So I stopped using the bare identifier ID, and I made everything specific. So I named things my ID, or follower ID, or candidate ID, and it makes it a lot easier. One piece of advice that I got from a talk by Leslie Lamport, a very opinionated piece of advice, is that the correct way of thinking about distributed systems is thinking about the entire system. So you shouldn't think about things like this node is the leader. Instead, you should think about it as this node thinks it's the leader for this term. Maybe there are other nodes that think they're the leader for different terms. Or in the case of commitment, I'm sure at least during development of the Raft algorithm, it would have been helpful not to think about terms as being committed, but this node thinks it's committed, and follow along and see what happens from there. So thinking about the whole system rather than trying to use these simplifying abstractions. If you're interested in Raft, a few other things you might want to check out. There's the Raft thesis, and there's analysis of Raft consensus. These are both very long. Analysis of Raft consensus is, I think, 50 or 60 pages, and the thesis is more like 180 pages of content. So you probably don't want to read them unless you want to implement Raft, and even then you might not. Like really, if you want a really detailed understanding of Raft and different options, then you might want to read them. If you do want to learn about basic Patsos, I recommend you check out those class notes. There's a 2-page explanation, which is pretty easy to follow. Egalitarian Patsos I talked about. CRDTs are a cool topic. The other one I just want to briefly mention, I talked about Byzantine fault tolerance, but there's another fault model that I like better, which is called arbitrary state corruption, which is where you don't assume that nodes are actively malicious, but they can kind of make mistakes. So things like the network might have a bit of corruption on it, or a node might have an if statement, but they accidentally run the else branch instead. Things like that, or that they have a single bit error in RAM. With networking problems, there's easy things that you can do, like adding a checksum, where that doesn't do anything to support a Byzantine node because they can calculate a checksum as easily as you can. Under arbitrary state corruption, there can be some similar things that you can do in terms of running the program, where you can deal with these single bit errors and things like that. But there isn't many papers on it. But I think I like that fault model better because I think it's more applicable to actual systems. And that's the end of the talk. Are there any questions? Yep.
So if you compare this algorithm to whatever Cassandra is running, I guess the obvious advantage of Cassandra's algorithm is that each node is a leader or something like that. Messages are sent through any of these star components, and then we don't have single point of failure, but then probably there are trade-offs which should be the advantages of this algorithm.
So a quick comparison with Cassandra. Cassandra has a new operation, a compare and swap operation, which they call lightweight transactions, which actually uses basic Patsos. For their main replication algorithm, they just use a last writer wins based on timestamp. So it's not a consensus algorithm, really. It doesn't have a single point of failure, or depending on how you're using it. If you're doing core reads and writes, for example, this doesn't either. Though, like you do have a leader, which is special, but if they fail, somebody else will take over. What Cassandra deals with, though, is scalability. So if you have more data than can fit on one machine, it also tells you which nodes are responsible for that data. Whereas with Raft, every node has all the data. It doesn't deal with scalability at all. You have to do that separately.
Yeah, but in Raft also every request goes through the leader, whereas in Cassandra it's like the load is distributed between each member.
Yeah, it does distribute the load, although the cost of that is that you don't have consensus. So you have last writer wins based on timestamp. So you could have multiple requests come in, they both say that they're successful, and then you end up with one of them winning, it's not clear which. The one that wins could even have been later, or sorry, the one that gets overwritten could have even been later in time, in real world time, if it had an earlier timestamp due to clock skew, for example. Questions?
I was going to ask if you know of any, how do I say this, like back and forth between the Patsos people and the Raft people. Like, has anyone who's worked on Patsos or a variant of Patsos commented on Raft?
I saw a talk where Leslie Lamport was asked what did he think of Raft, and about the understandability and all that kind of stuff. And his response was that he had heard of Raft, he hadn't read the paper or studied it in detail. His only comment was, if you are comparing the understandability, then you should compare similarly rigorous explanations of it, rather than kind of simplified explanations or things like that. You should compare, I think maybe he was getting at, compare a proof of the algorithm and see which one is simpler, or how they compare there. Because it can be very easy to come up with a simple and intuitive explanation that isn't right, or leaves out some of the details. So that might be easy to understand, but the full thing might not. So that was his comment. Yep.
I was wondering what your implementation is
For fun and learning, and maybe using for something later on, but right now just implementing it. Yeah. Any more questions?
Has this formally been proved?
Has it formally been proved? Yes. In the thesis, they include a proof in the language TLA plus temporal logic of actions, I think. Yes, they do include a proof. Another question?
So I believe there's a popular Go implementation of
Go Raft, yes.
Go Raft, yeah. So in a library like that provides this algorithm for a particular language, what's the boundary of like what it defines for you? Does it define how the log is stored and how the network, like what the network transport is, or does it leave all that up to you, or?
With the library, where are those boundaries between what it does and what you do? I don't know about Go Raft. I looked briefly at one of them, and I think it mostly tries to leave it up to you about things like storing the entries. in my implementation, I made it completely pluggable. Like that was part of having that network class where I could swap it out for a real network later on by using a fake network. Made it easier. I did similar things for persistence, where I had things where it would persist it, but really I stored it in memory, but I could decide to kill the instance and remake it, but still with the persistent stuff. So in mine at least, I made it so that you could do the networking, you could do the log stuff, and it would just tell you when things were committed and when you should apply things, and you can give requests to it. But that's kind of up to the library author. It's kind of fuzzy because there's lots of things where usually you want to hook it into your own networking, but it's easier if it does it all for you. So there's a trade-off there. Yep.
If you were to implement this, is there an exhaustive list of like pathological failures that you test against?
List of pathological failures.
Like as far as actually like most of the examples that you showed where certain nodes fail at different points in leader elections.
Yeah. I would say use your imagination at first, and if you want something more rigorous, I think maybe it's in the proof, maybe not. But one way of doing it is, as you are replicating these things, as you're running the algorithm, just do random operations, random message dropping, reordering duplication, failure, all that kind of stuff. But also inspect the state of each node to know when it thinks things are committed. And if you ever have a case where a node thought something was committed, but then it didn't eventually go through, you know you have a problem.
Yes.
Yep, that's one of it. One thing that Google did for Chubby, their locking service, similar to Zookeeper, for those who know that, they ran their system and they simulated lots and lots of failures, and then they stopped doing the failures and made sure that the system eventually recovered if you did something similar to that, while also remembering the invariant that committed things must always be committed. I think you would get pretty far with that. Yep.
I was going to make a comment about the proof of Raft when you talked about TLA plus. That system is a model checking and property checking tool designed to test properties of systems. Information is actually written by Leslie Unport,
Yeah.
who invented Patsos. It's the same person.
Yeah.
So it's sort of like an interactive. It's not a mathematical proof, but it's a way to verify the properties of the system.
Yeah, you define certain invariants in there, and it will check it and verify it. And one other quick comment about it is that in the paper they describe it using method calls to these remote objects or the remote nodes. In the proof, they actually did it with message passing though. Just a fun fact. Any more questions? All right, cool. Thanks.